how would you do your tournaments? Would you have the winner always prevail, usually prevail, or 51% goes to the winner and 49% goes to the victor?
Always
Or the loser? Yeah, I think the winner could almost always prevail in this case because, I mean, there is this slight local optimum here, but you can probably find your way over to here and then get down into here. So you can handle convex optimization really well without a lot of exploration. Whereas if you have some kind of a surface that looks like this, do you see that now exploration becomes really, really important? So you want to make sure that there's only very weak pressure leaning towards the most fit members of the population and a whole lot of generations and maybe a big population, right? In the previous one, what would your population size be? Maybe 2, maybe 3, a few would be fine. In this case, I'd say a population of maybe 50 would be good, maybe 100. Because you want a lot to kind of sample all over the space so that you can kind of evolve towards the more fit locations of the space. Now, having gone through all of this, what does the space look like in, say, sumo billiards? That's kind of the problem. I really don't know. So what do you do? Short answer is you should probably have a population that's not too small. You want to put not too much pressure on the tournaments to win, and then you just run it for a darn long time, and it should probably work, right? That's really kind of the best we've got. The other thing is, if you can put those parameters into the genome, then maybe they'll evolve, right? Because the members of the population that survive probably survive with reasonable parameters in their genome. Therefore, those can drift towards better places too, so maybe it'll learn how much pressure to put on and things like that. So I want to talk a little about how to do that. Let me bring up the instruction page. AI schedule, is this one 4? Okay. So actually, I want to get into, for selecting the most fit chromosomes. Okay. In this particular assignment, I provide this method called controller.rankAgents, right? And this basically ranks all the agents and tells you which ones are the most fit. I need to be clear, this is not actually the way it's usually done with a genetic algorithm. So in this case, the controller.rankAgents does a pairwise tournament between every single member of the population and reports to you a ranked list of how often they won, right? What's usually done in a genetic algorithm is they'll do what's called a tournament, but a tournament really only involves 2 people. So they'll say A equals population dot random. That means pick a random member of the population. B equals population random. And then they'll say, let's see, tournament A dot B, A comma B. Winner equals tournament A comma B. And then they'll say something like, let's see, Boolean A wins A comma B. How about that? If A wins, then with 60% probability, kill B. Else kill A. And then the same thing here. 60% probability, kill B, else kill A. Okay. So the idea of this is usually a tournament just means you pick two randomly out of your population. So man encounters bear, man and bear fight, bear has big claws, man dies, right? Except every once in a while, the man's carrying a sharpened spear, sticks it in the bear dies. And this lets evolution progress slowly. Think about it, if you will. How does this type of tournament, where you just pick two members of the population and you do a tournament, differ from a full-on tournament where you battle everybody with everybody else? Well, first of all, which one's more like real life? I'm going to say probably this one, because you kind of encounter other members of the population randomly. Although arguably you could say that it depends on what situation we're talking about. If it's fighting against a creature, this happens. If it's I don't know, fighting over resources, pretty much the king is the only guy who becomes the king, or the guy everyone supports is the only one who becomes the king. Maybe that's more like doing the full tournament, right? Maybe. I don't know, you could argue it both ways. This is the way I usually like to implement evolutionary optimization, because it seems kind of random and it kind of injects a lot of diversity into who survives and who doesn't, because it depends heavily on which two you randomly pick to do the tournament, right? Also, these tournaments are really cheap. If we do the pairwise tournament between everybody, well, that's actually n squared number of tournaments. So this is going to mean each generation takes a lot longer to do, or each iteration takes a lot longer to do. So if you actually don't want to call my rank agents method, but you just want to do a single tournament, I think that's probably going to produce better evolution. But it turns out this assignment's so easy that no matter how you do it, it's going to beat Bob. So I guess it doesn't matter. Nevertheless, when it comes time to test you on this, I want you to know this is what is meant in genetic algorithms when they say tournament-based selection. A tournament means you pick two members randomly from the population, they have a tournament, and the winner of that tournament usually wins. But they never do it such that the winner of the tournament always wins, because of what we've just been talking about. Okay? There's another type of way of doing, of measuring fitness in genetic algorithms called fitness proportionate selection. The idea of fitness proportionate selection is you run through every member of your population and you measure the fitness of every member of the population, and you give it a number somehow, or maybe you rank it. And then with probability proportional to its fitness, you let it live. Does that make sense? Okay, so fitness proportionate selection versus tournament selection. Which one is better? Or more specifically, think about it for a minute and give me some properties of how does one of these differ from one of the others in its effect on what it will do to a population of evolving genes. I'll give you 20 seconds to think of a difference.
Maybe one produces a generalist and the other one produces a specialist.
Okay, what do you mean by generalist and specialist?
A generalist could possibly be good at more than one thing, while a specialist is really good at one thing, but bad at others.
Okay. So I think you would be saying that the fitness proportionate selection is specialist and this one's generalist. Am I right? Maybe so. I'm not sure.
Just an idea.
Yeah. Okay. Yeah.
Well, in the tournament selection, like, you could have a case where the winner's only like barely better than the opponent it beats, and so the opponent then has a higher probability to die than the winner. But if it's just purely fitness based, then it's going to be more of like an even spectrum.
Okay.
Because like goodish ones aren't going to get knocked out by the best ones.
So you're saying if you're on a slope that looks like this versus on a slope that looks like this, so between red and blue and red and blue, in the steep slope case, fitness proportionate selection is going to almost certainly kill off red and almost certainly let blue live. Whereas in this case, it's almost 50-50 as to who lives because blue is only slightly better than red. Okay? In tournament selection, they're going to have a tournament and blue is going to win because blue is better. And then with 60% odds, blue is going to live and red is going to die. And so in both cases, the evolution leans towards blue, but we lean towards blue a lot more strongly in the fitness proportionate selection case, whereas in tournament selection, no wait. Well, in the fitness proportionate selection version, the pressure is higher the pressure is proportional to the slope. Whereas in tournament selection, the pressure is the same no matter what the slope is. We're always trying to get to the better one. I think that's pretty insightful. I think that's right on. Now the question is, which is better in general?
Once again, it depends on what you're trying to accomplish.
Yeah, again, this comes back to what is your error surface like? There are reasons why this is better and there are reasons why that is better. So again, I don't know. In my opinion, this seems to happen a lot where you get on these plateaus and it's important to make some kind of progress or your progress just stalls. I tend to like tournament selection because it moves at full speed no matter what the steepness of your slope is. So it's going to evolve that way in both cases, but this way it's going to evolve that way rapidly. I consider probably the biggest problem with genetic algorithms to be that they're just so darn slow. It takes them forever to get some good stuff. So I tend to lean towards tournament-based selection instead. The selection I'm having you do, where you do a full tournament, is kind of a hybrid of both types. Do you see that? I've never actually read anywhere that they do a full tournament. I made that up. But because it's a genetic algorithm, you can do pretty much whatever you want. And so I've invented the full tournament, and maybe it'll work. I'm sure someone invented it before me. I'm not trying to take credit. I'm just trying to say that these are the two main types of fitness selection. The main two types of selection in genetic algorithms are fitness proportionate selection and tournament-based selection. Okay. Feel free to code up whichever type you like, or use my full tournament version if you like. Okay. So let's talk about a few other words here. These are some things you don't have to code up in this assignment. One of them is cloning. How do you suppose you do cloning?
Just copy the same genome in multiple times in your...
Yeah, the idea of this is it's basically asexual reproduction. This is what bacteria does. It takes its genome and makes a copy of it. Now, generally this is considered bad because cloning essentially makes another one of the very same type, and that reduces the amount of diversity in your population, right? That could be good if you're really close to the global optimum, then you don't want to mutate too much. So it could kind of keep around the best answer, but it's generally considered that crossover is a much better way to go because it promotes diversity, and genetic algorithms depend heavily on diversity. Okay. The way I see it is, hey, why not do both? Because if you're going to do a genetic algorithm, why not just code up everything under the sun, and then if you need something, maybe it'll just happen and maybe it'll work out. Does that make sense? So feel free to do fitness proportionate selection, tournament-based selection, cloning, crossover, interpolation, extrapolation, and all these different things. And the more weird stuff you do, the better your algorithm gets. It's the general intuition there. Okay. So we've talked about interpolation, extrapolation. What about a catastrophic mutation event? What do you think that is?
The sun has a gigantic solar flare and everything changes at once.
Yeah. So This was mentioned in our last lecture, but sometimes there's cases where one mutation makes it worse and another mutation makes it worse, but if both of them happen at the same time, suddenly that's really good, right? Well, how do you ensure that there's some probability of that happening? Well, maybe with some random probability, you do a whole lot of mutation. So instead of picking one member of the chromosome, you pick 50 of them and you change them all. Or you take all of them and add a random number to it, or something like that. If you're going to mess with all of them, you probably want a very tiny deviation. I don't know. There's not really any rules. Do whatever you want. Maybe you could pick however many members of the gene you want and mutate them. Okay. Speciation. In the physical world, you don't get a lot of humans mating with worms. Now, that, except in the case of your brother-in-law or something like that, I know. But the thing is sexual reproduction only works when two things are sufficiently similar to each other. So if you want to create species and only take things that are sufficiently close to each other before you generate children, some papers have claimed that improves evolution and makes it work better. Why would speciation maybe help?
You're going to at least find the local optima faster.
Why?
Because if you focus on, so if you've got a species that's in a certain, presumably the species lives around a certain area of the terrain, right?
Uh-huh.
If you only focus on development within that species, they're going to find the low point of that terrain pretty quickly. But if you've got a species here, and a species over here, that
Okay.
that may be more like the continental thing, though.
Yeah, in fact, they're really similar. Speciation and continental separation are kind of the same thing. Yeah, I guess the idea is you want there to be a lot of diversity, but you also want to refine your local place, right? You want to get to the best place around, but you don't want to necessarily kill exploration going elsewhere. So as long as you can separate like that, this makes it quite possible to nail down the best place around here while simultaneously wandering all through the space. I've seen quite a few papers that claim that speciation or continental separation drastically improve genetic algorithms. So if you want to, you can improve yours in that way. The idea of continental separation is rather than doing it based on the location of the genome itself, you just sort of arbitrarily divide them into groups, and you do it in, you evolve these together and you evolve those together and you see what happens. So speciation is kind of based on the gene itself. This is based on something unrelated to the gene, I guess. Okay, so we talked about multiple point crossover, different types of selection, and feel free to make stuff up. Okay. What else is there to talk about this? I think as far as testing goes, it's really important for you to understand that there are good reasons not to always let the best member of the population survive. If you do this continental separation or speciation thing, then maybe it is okay. Maybe it's better to let the best member of the population survive, right? If I were to ask you what key elements are necessary for evolution to occur, what would you say? Got to have diversity, which implies you have a population greater than one. I guess that goes with diversity. What else do you need?
Mutation.
I think mutation promotes diversity, so I think I'm going to say those are the same thing. No?
Time.
Well, I guess mutation. I guess you have to have change. Even if you have diversity but nothing ever changes, you keep getting back the same members of the population, that would be death. So you got to have change. I guess that did add something to it. Time. You got to have some kind of pressure towards betterness, right? If there's no selection of any type, if you just mutate, what's going to happen? You'll randomly explore the space, so what? The only way it makes progress is if the bad members of the population die, or the good members of the population are more likely to have babies, or something like that. Okay. What about if you do evolution with no population limit? You just let the population grow and grow and grow. There's no death. Would that work?
If you have a powerful enough computer.
Yeah, so there's the major problem is your population gets really big. Now how do you handle the computation? What if for some reason it's parallel? You have unlimited number of processors. That is totally the right thing to do, isn't it? Or is it? Well, it depends on a few factors. How are you selecting who produces children? If you pick two random members of the population, do you see that'll actually slow you down to keep around the dead weight bad members of the population? Whereas if you kill them, evolution happens faster because the members of the population tend to be good, and so you tend to have better children, so it actually evolves faster. Can you see why maybe death is even a good thing? I don't know. I think death may be a good thing. I don't really want to live forever. Maybe I do, but I don't want anybody else to live forever because they'll take over the world and ruin my life. So I like death. Death is good. Okay, somebody's going to cut that out of the video and post on YouTube. Dr. Gashler saying, death is good. That's going to be terrible. Please don't do that.
I think you get all the primary points from the X-Men movies.
Yeah, pretty much, yeah, okay. Except for the fact that no mutation is going to make spikes shoot out of your hand. That's just so, there's no way. Okay. And any questions on how to code this up? Do you want me to look through my code again and show you which classes you need to look at and which ones you can safely ignore? Or you already got it? Covered well enough? Okay. Awesome. I think I'm done with evolution. Let's do this assignment and move on. Cool. All right, new topic. Let's talk about neural networks now. Okay, we talked briefly about neural networks. I said they're a black box. Numbers go in, numbers come out. A neural network is a function approximator, meaning we assume some function already exists that we want to approximate, and if you get the right weights into the box, the neural network gets pretty close to that function, and then itself becomes a function, and you can use it to approximate whatever function you want. We're using it in assignment 4 to approximate the controller of a sumo ball, and there's something to do. Okay. Let's talk about how they work now. So let's start with a perceptron. The idea of a perceptron is a bunch of numbers go in and one number comes out. Let's suppose the numbers happen to be 4, 2, and 1. And there are weights on these which happen to be 0, -1, and 3. A perceptron calculates its output by using a linear combination of the inputs. Basically, it's 4 times 0 plus 2 times -1 plus 1 times 3. So I'm going to draw a summation symbol in here to indicate that this is, well, the equation is y is equal to the sum of x sub I times w sub I. I guess that's the sum over I. So here, the output is going to be, let me give you an arrow there. 4 times 0 is 0, plus 2 times -1 is -2, plus 1 times 3 is 3, 1. Okay. This perceptron outputs a 1 when the numbers 4, 2, and 1 are fed into it, right? What if we change that 2 to a 3? Now what does it output? -3, 3. Now this becomes a 0. There. Okay. Do you get a perceptron? It's very simple. Numbers go in, they get multiplied by the weights, which we draw as being on these lines. They get summed up when they're in the unit, and then they come out. Okay. There's a reason for this structure. The reason is inside the human brain, our brains are made up of something called neurons. Do you know what a neuron is? A neuron is a brain cell. Let's take a look at Google. Let's see, neuron. There's all kinds of diagrams for neurons out here. There's one. Here's a diagram of a neuron. A neuron has what's called the soma. The soma is this main body of the neuron. This is kind of the circle that I drew here in this perceptron diagram. So this is the soma. And a neuron has a bunch of lines that go into it. These are kind of these, well, these are dendrites. Dendrites are these elongated fingers that feed into the soma. And most neurons have one axon coming out of them. That's not true with all of them. Some of them have two axons. But think of the axon as the big gun. The soma is connected to this axon, and it sends an electrical pulse out of this axon. The axon happens to be wrapped in these myelin sheaths. That's kind of the insulation around a wire. The whole notion of this axon is dendrites are the inputs, the axon is the output. Okay? Your brain cells communicate with each other through electrical pulses. So all your little brain cells are sitting there firing at each other, just pew, pew, pew. And these fires are voltage potentials. And the voltage potentials sort of shock, they send a shock down the axon. And the axon of every neuron is connected to the dendrites of a bunch of other neurons through a synaptic connection. And as these little shocks come into the neuron, the soma accumulates these voltage potentials. So you can think of it as, once you get shocked enough, you get excited and you start firing. So it's kind of like you just sit there, get shocked some more, and once you build up, you push over the top, then you fire, bam, and then you're gonna trigger a whole bunch of other neurons, if that makes sense. And by you, I mean some random neuron. You have about 80 billion of these in your head. You have approximately 100 trillion synaptic connections between dendrites and axons inside your brain. And let's see, that 80 billion number I mentioned is only counting your cerebral cortex, doesn't count your and we'll talk about that later. Anyway, point is, you got a whole lot of these. They're all shocking each other, and somehow encoded in all of that is the amazing cognitive abilities that you as a human have and do with your brain. And that's kind of cool, right? So in order to try and simulate this, we invented a very simplified model of it, which I have drawn somewhere. Here it is, which is the perceptron. And the idea of a perceptron is numbers go in, get multiplied by these weights. This is what happens at the synaptic connection. The synapses essentially affect how the voltage is allowed to get through into those dendrites. All the values get accumulated inside the soma, so that's what this summation is, and then it fires off a number, and you got a number here. The reason we use a number is sort of representative of the frequency at which these pulses are firing. So in an actual physical neuron, these electrical spikes are coming in at some frequency, and it's coming out at some frequency. Rather than waste our time simulating that, we could just put a number here that represents the frequency, and then this becomes a very, very loose model for a neuron. Now the question is, what if we have a whole bunch of these? Can we make a big brain? Wouldn't that be cool? Okay. Well, that's the idea of an artificial neural network. So let's take a whole bunch of these things. Let's suppose we have two inputs. Call it x1 and x2. Might as well give all my inputs these axons and connect them to the dendrites of all of my neurons. And maybe I've got 2 more neurons. And maybe I finally want to get 1 output. And I'll call that Y. I want Y1. This is what we call an artificial neural network. So an artificial neural network is made up of a whole bunch of these perceptrons.